In the last video that we did, we looked at polynomial long division, and when we finished, we had that idea with the factor theorem and the remainder theorem that essentially said if you're dividing a polynomial, say x cubed plus 2x squared minus 4, and you're dividing it by x minus 1, before you do the division, you can actually check what your remainder is. All you do is, if this is x minus 1, then in the form x minus k is equal to 1, and we just take that 1, plug it into the polynomial, and whatever we get should be our remainder. So for the purposes of this, if we plug in 1, we get 1 plus 2 is 3 minus 4, negative 1. And we said we could use that as a guide when we do our long division. Go through all the long division, make sure the remainder you get is negative 1. Today we're going to kind of expand on that a little bit and use it to solve other types of problems. The ultimate goal here is to be able to find all the zeros of a polynomial. So say if we had x to the fourth plus 3x cubed plus 9x squared minus 7x plus 4. We're not going to solve this one, but the idea is ultimately we want to be able to look at polynomials like that and say, well, that's a degree 4, which means it'll have 4 zeros, and we want to find all 4 zeros, hopefully without just looking at our calculator and using some mathematical tricks. And today we're going to run through all of those tricks. The first trick we can actually use is the remainder theorem that we've been using before. Because we said, well, if we want to know if something is a factor, we can just plug it into the polynomial. If we get 0, then the remainder is 0, which means it's a factor, which means it's a 0. But the problem is, if I have something like x cubed minus 1, and I'm dividing it by x minus 1, well, then it's really obvious that if I plug in x equal to 1, the remainder theorem will give me 0, and 1 is a factor. That one's easy to see, but what happens when we have a polynomial that looks like 3x cubed plus 7x squared minus 9x plus 5? And I want to try to find all the zeros of that. There's different tricks we can do. The first one we want to look at is what's called the rational root test. And all the rational root test says is if you have a polynomial and the coefficients are integers, 3, 7, 9, 5, those are all integers, so we're good. If you have a polynomial and the coefficients are all integers, then if you have a rational root, it has to be of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. It sounds a little confusing when you first hear it, but essentially the idea is we have a polynomial with integer coefficients, so we want to find all possible rational roots. So the values of p have to be factors of 5. So what are the possible values of p? Factors of 5 are plus or minus 1, make sure to account for negatives, and plus or minus 5. The factors of q, the factors of the leading coefficient, well, the factors of 3 are plus or minus 1, plus or minus 3. Now, those are not my factors, those are the possible factors once I do p over q. So now, find all possible quotients p over q. So let's see if we do that. We get 1 divided by 1, which is plus or minus 1. 1 divided by 3, which is plus or minus 1/3. 5 divided by 1, which is plus or minus 5. And 5 divided by 3, which is plus or minus 5/3. And now essentially what the theorem says is, if there is a rational root to this polynomial, it has to be one of those 8 right there. Plus or minus 1, 1/3, 5, or 5/3. The trick is to recognize the theorem doesn't tell you the rational roots or give you all the roots. It simply says if there happens to be a rational root, then it has to be one of those. And you'd have to check all of those to see if they're roots. They might be, they might not be. You might get all your roots listed here. You might get 1, 2, 3. You never know. You just have to run the test. And as far as it goes, the way this works is we kind of build as we do this. If these are possible rational roots, well then if I want to know if they're actual roots, I could just take them, plug them into the polynomial using the factor theorem or the remainder theorem. If I get 0, it's a root. If I don't get 0, it's not a root. We're not going to take the time to do this right now because it would take too long on this video to run through all of those. But essentially, we just keep applying the remainder theorem. Plug in 1, see what you get. Plug in -1, see what you get. Plug in 1/3, see what you get, and so on. Anything that gives a 0 is a 0. If it doesn't give a 0, it's not. And again, the key point is, this may not give you any of the roots. This doesn't guarantee that these are roots. It just tells you if there's a rational root, it has to be one of those 8 right there. So to kind of work through this and use it, going back to the one we had before. Well, maybe we'll make it slightly different. We'll look at x cubed minus 8. I want to find the possible roots of x cubed minus 8. I know there'll be 3 of them because it's cubic. So let's see. It's a polynomial. Coefficients are both integers, 1 and 8. So I can use the rational root test. So let's see. The possible rational roots are p over q. P has to be a factor of the constant. Factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Q has to be a factor of the leading coefficient. So the possible values of q, well, that's just plus or minus 1. Now we take all the quotients, p over q, but in this case, since q can only be 1, p over q has to be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Now we have 8 possible rational roots. We would use the remainder theorem, plug all 8 of them into here, and see if any of them give us 0. In this case, it should be pretty obvious. Positive 2 will actually give me 0. If you plug it in, you get 2 cubed minus 8, which is 8 minus 8, which is 0. So that's definitely a 0. Now what we do is we go back to what we did before, polynomial long division. I'll take this polynomial. If 2 is a root, then it's associated with the factor x minus 2. So I'll take this polynomial, I'll divide by this factor, and I'll turn my cubic into a quadratic. Once it's a quadratic, well then I can just solve it with the quadratic formula and find the other 2 roots. So, to kind of see how this works, we'll do our division. Keep in mind we'll need placeholders and all that. So we'll have x cubed plus 0x squared plus 0x minus 8 divided by x minus 2. And now really quickly, because we've done this before, feel free to fast forward through this part of the video if you've watched the other ones. Multiply x by x squared to get x cubed. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. Switch the signs. That becomes negative. This is positive. That goes away and I get 2x squared. Bring down to 0x. Multiply x by 2x. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Switch the signs. That becomes negative. That's positive. That goes away. 0x plus 4x is 4x. Minus 8. What do you multiply x by to get 4x? 4. 4 times x is 4x. 4 times negative 2 is negative 8. Switch the signs. That becomes negative. That becomes positive. And we get 0. Which is what we knew we would get because x minus 2 is a factor. But the point is, now I've turned this cubic into a quadratic. Now all I need to do to find the other 2 roots of the cubic is to solve this quadratic. For that, sadly, because of the limitations of this video, I'm kind of out of room, so I have to erase all this work. But now, I just need to solve that quadratic. So, it's not going to factor. Plug it into the quadratic formula. So really quickly, I'll get negative b, which is 2, plus or minus the square root of 2 squared, which is 4, minus 4 times a, which is 1, times c, which is 4. All over 2 times a, which is 1. That gives me negative 2 plus or minus the square root. 4 minus 4 times 4 is 4 minus 16, which is negative 12, all over 2. We can simplify this out. We recognize it's a complex number. And I get negative 2 plus or minus 12 is equal to 4 times 3. So root 4 times root 3 times I, all over 2. Which becomes negative 2 plus or minus 2 root 3i, all over 2. And now just really quickly simplify it and put it in standard form. There's a common 2 everywhere. And then when I split up the fraction, I'll get negative 1 over 1, which is negative 1, plus or minus root 3 times I. Now that gives me 2 solutions to the quadratic. Up here we found one more solution, and that gives me all 3 solutions of the cubic that we had. This is actually how we want to go about doing this. Taking a given polynomial, finding the possible rational zeros using the rational root test, testing them. If any of them gives me a 0 using the factor theorem, doing the long division out, which I had here before I erased it, which will reduce my polynomial, and once my polynomial is reduced enough, we'll then just throw it into the quadratic formula and get solutions that way, and ultimately find all possible roots of a given polynomial. We're going to expand on this in the next video, but this one's getting a little bit long, so we'll stop here, and then we'll discuss these complex roots in the next video.